Exploring Simulink Design Verifier for Flight Controls. Hi, I'm Natasha. I'm a student of computer engineering at NIT Surathkal. We were given this project by Moog India for us to have a better understanding of Design Verifier. We were given two problem statements. One, priority circuit for an autopilot mode transition logic, and two, an on-ground circuit for an aircraft. Moving to problem number one. We had to design a circuit to prioritize the inputs to an autopilot mode transition logic and validate the design using Simulink Design Verifier. As per system requirement, an input 1 would give a true output or Boolean 1 output if that input was true and all other inputs of higher priority were false. For example, for output 6 to be true, input 6 must be true and inputs 1 to 5, which have a higher precedence than 6, must be false. Assuming the booleans 1 and 0 to be integers, if sum of the inputs is greater than or equal to 1, then the sum of the outputs equals 1. Also, if sum of the inputs equals 0, then sum of the outputs equals 0. We started off with a rough design on paper, which was later translated into this Simulink model. Moving on to problem 2, on-ground circuit for an aircraft. This logic, based on weight on wheels, uses three triggers: weight on wheel nose, weight on wheel right, and weight on wheel left. If any two of the three weight on wheels trigger are true, the plane is said to be on ground, or on ground is true. Alternate on-ground logic uses CAS, calibrated airspeed, and RADALT, radio altimeter values, to judge if the aircraft is on ground or not. System requirements say that if CAS is greater than 70 knots or RADALT is greater than 150 feet and for a duration of 2 seconds, on ground equals false, that is, the aircraft is in air. If CAS is less than 60 knots and RADALT is less than 100 feet and for a duration of 1 second, then on ground equals true. We reduce the number of frames for faster results, but the duration can be extended to 1 and 2 seconds. Our first design used independent hysteresis for CAS and RADALT, but this was proved wrong by Design Verifier. We made some changes to the same and combined CAS and RADALT into a single unit. This design was tested and Design Verifier results showed that it satisfied all system requirements. Let us look at a demo now. What we have here is our design for problem 1. The priority block prioritizes the inputs. Each of these subsystems is a combination of OR, NOT, and AND blocks. This model is tested using the verification subsystem, which clearly defines our system requirements. As can be seen, the booleans have been converted to integers and then summed up. We have used implies block to check for true condition. This block can be obtained from the Simulink library under Design Verifier. Simulink Design Verifier, Verification Utilities, and then implies. This here is our design for on-ground circuit logic based on weight on wheels. Down here, we have our design 1, which failed when tested by Design Verifier. This is the hysteresis block. The verification subsystem is where we defined all the system requirements. This is our final design which satisfied all system requirements. We have used a series of switch blocks and delay blocks to get the desired results. We will be uploading a set of files with Design Verifier modules as benchmark problems. Thank you.